Now, just like individual real numbers, just like scalars, vectors can be added together, can be subtracted, and can be multiplied by numbers. That's what we're going to do today. We're going to talk about vector addition, subtraction, and scaling. We're going to look at what those actions look like when the vector is represented graphically, and then we're going to look at what those actions look like when the vector is represented using components. Then we're going to take a brief look at a way of representing vectors that is slightly more common in physics, which is to use something called the standard basis vectors. Vector addition. Just like numbers, two vectors can be added together. Now, why would we want to add two vectors together? If the vectors that we're adding represent, for example, two displacements, then adding the two vectors is what would tell us where we would end up if we walked along these two vectors in sequence. For example, suppose that we had one vector that represented a movement to the north 4 miles. And suppose that we had another vector that represented a movement to the northeast by 5 miles. If I called the first vector v with a vector arrow over it, and the second vector w with a vector arrow over that, the sum of those two vectors would be describing the movement directly from the initial position of v to the final position of w. Now, if our two vectors represent two velocities, in this case, what does it represent when we add these two vectors together? This represents a combination of these two velocities. For example, suppose you have a plane which is flying, and the plane has some velocity of its own. But if that plane suddenly encounters a strong wind which is blowing in the opposite direction, then that wind blowing against the plane is going to change the plane's velocity unless the pilot does something to compensate. So it will slow the plane down, and that will result in a shorter overall velocity vector for the plane. If the two vectors being added together represent two forces, what can the sum be used to represent? This is what is called in physics net force. The combination of those two forces acting on the same object. For example, suppose that we had a box, and somebody was pushing the box to the left, and someone was pushing the box toward us. Then those two folks acting together would be effectively exerting a force in this blue direction. That would be the combination of their two forces. A force which is a little bit toward us and a little bit to the right. Now, it's the first way of thinking about adding two vectors together that provides us with a graphical technique for finding the sum of two vectors. If I want to graphically add together two vectors v and w, then I can do that in 3 steps. The first thing that I do is I draw the first vector v with its tail at the origin. So this represents starting from the origin and following the path called v. Once I have followed the path called v, I'm going to immediately follow the path represented by w. So not restarting at the origin, but starting from the final position of v, I'm going to draw w. Draw w with its tail at the arrowhead of V. Travel along V and then immediately travel along W. What, therefore, will the sum be? V plus W is the arrow stretching from the origin to, in this picture, wherever the arrowhead of W ended up. Let's try out the graphical method quickly to sum up these two vectors where V is equal to 2, -1 and W is equal to -2, 3. To begin with, I'm going to draw the vector V with its tail at the origin. So I'm going to go 2 units in the positive x direction and 1 unit in the negative y direction. So here is the vector called V. Now I'm going to draw the vector -2, 3. But I'm going to draw it so that the vector originates from the arrowhead of V. So from this position, I'm going to go 2 units in the negative x direction, which will bring me back to x equals 0. And I'm going to go 1, 2, 3 units in the positive y direction. So that points me right here. Now the sum of these two vectors is the one that goes straight from the origin to the arrowhead of W, drawn in this manner. So V plus W would be equal to the red arrow in this picture. Now from the picture, we can actually determine the components of V plus W. Now notice something interesting about the components of the sum of these two vectors. The x component of 0 in our final answer could also be found by taking the x component of the V and adding it to the x component of the W. 2 plus -2 is indeed equal to 0. And similarly, the y component of our final answer could be found by taking the y component of V and adding that directly to the y component of W. -1 plus 3 is indeed equal to 2. So when we have a vector which is expressed in components, there is a tremendously straightforward way to add the vectors together. And that's to do what's called component-wise addition. Component-wise addition of vectors says that if you have a vector V and W, that if you have vectors V and W, and you want to add them together, all you have to do is this. Add together the two x components, and then separately add together the two y components. Component-wise addition. In other words, add the components individually. This is what really makes vectors great. It's very rare in mathematics to have formulas that are this nice. Let's practice adding vectors component-wise in the following example. Here we have the vector V, which is 3, -2.5, and we have the vector W, which is equal to 5.1, 2. Because these are not exact values, it would be tremendously difficult to accurately represent them in a graph, which is where being able to do this arithmetic by hand without using a graph is so valuable. The formula says that if you want to find the sum of those two vectors,
it's going to be super easy, barely an inconvenience. Oh, really? Yeah.
You can take the sum of the two x components, 3 plus 5.1, and the sum of the two y components, negative 2.5 plus 2. Result 8.1, comma, negative 1/2. Full stop. That's it. It's over. Isn't that wonderful? How often is it that easy, folks? Really, really nice. So even though graphical addition of vectors is a thing, it's almost immediately thrown into the bin in favor of component-wise addition, simply because component-wise addition is so much easier than graphical addition. Now, if you want to subtract two vectors instead of adding them together, that is something that can also be done component-wise. If you want to take the difference of a vector v and a vector w, if you want to calculate v minus w, then you can take the x components of v and subtract the x components of w, and you can take the y components of v and subtract the y components of w. Component-wise subtraction. For a quick example and a quick explanation of why we might want to subtract vectors, let's consider the following exercise. We have got 3 people all pushing on a table. Now the force exerted by the first person is given by the vector 2, negative 1. The force exerted by the second person is 3, 0. The force exerted by the third person presently is not known. However, what we do know is this. The net force that results from all 3 people acting on this table at the same time is 0, 0. So basically, all 3 of them are completely canceling out all of their work, and the table is not moving at all. So the question is, what is the force exerted by the third person that is canceling out the efforts of the first 2 people? So we're told that the net force, the total force, is equal to 0, 0. And what this means is that if we add the forces of all 3 individual people together, the result of those 3 forces being added together is equal to 0, 0. So what I don't know in this expression is the third force. That's what I'm trying to find. And so to figure out the third force, what I'm going to do is I'm going to take 0, 0, and I'm going to subtract force number 2 from both sides, and I'm going to subtract force number 1 from both sides. So let's take 0, 0, the vector 0, 0, and subtract the vector f2, which was 3, 0, and subtract the vector f1, which was 2, negative 1. This is something that we can do component-wise. So I can take the x's and subtract those, 0 minus 3 minus 2. And I can take the y's and subtract those, 0 minus negative 1. So as a result, I can find the force exerted by the third person is represented by the vector negative 5, positive 1. Subtraction. Just like addition, it can be done component-wise. The third vector operation that we're going to look at today is what is called scaling. Scaling is what we call multiplying a vector by a single real number. And just like addition and subtraction, scaling again is a component-wise action. Suppose that I wanted to take a vector represented by v with an arrow on top of it and multiply it not by another vector but by a real number. Then all I have to do is multiply the x component by that number and multiply the y component by that number. Once again, I want to emphasize that this is not a technique for multiplying one vector by another vector. That's a little bit more involved than the operations we're doing today. And so we're going to be talking about multiplication of 2 vectors tomorrow. Now let's do an exercise to not only practice scaling, but to see what effect scaling has on a vector. To begin with, they give us the vector -2, 4, and they ask us to sketch the graph. So I'm going to graph -2, 4, which is 2 units in the x direction and 4 units in the y direction. So that would be right here. Here's the vector v. Next they're saying take your vector v and multiply it by the real number 2. Find 2 times v. Now component-wise scaling says that if you want to take 2 times the vector v, then all that you have to do is take 2 times each component. 2 times -2 and 2 times 4. Result, -4, 8. So the vector 2v would be hereabouts. Notice that in this same sketch, the original vector v would be located right here. So notice something about 2v. When we scale the vector by the number 2, the result points in the same direction as before. It's just twice as long as it used to be. Now, based on that, you can probably already anticipate what's going to happen when I take 1/2 and multiply it by v. 1/2 times v, component-wise, can be found by taking 1/2 times -2 and 1/2 times 4. Result, -1, 2. So if I were to graph that on the same axes as before, then I would get the vector which stretches to -1, 2. Same direction as v, but now it's only half as long as it used to be. Now if you had to guess, what do you think would happen if I took the vector v and multiplied it not by a positive number, but by a negative number? For example, -1. If I scale component-wise by -1, then the -2 in the lead is going to get changed into a +2, and the 4 in the back is going to get changed to a -4. So if I were to graph this vector on the same axes as all these other vectors, I would have to travel 1, 2 units in the positive x direction and 1, 2, 3, 4 units in the negative y direction. So that would position me right here. -v has the same length as v, but points in the exact opposite direction. And what if I combined 2 of those actions? What if I multiplied by 2 and also by -1? Result, multiply by -2. If I do the component-wise multiplication, then I get the result +4, -8. And so if I graph these on the same set of axes, oh, I'm running out of colors. What am I going to do? Pink. Okay, pink. Then this one is going to be twice as long and point in the opposite direction. So that's the purpose of scaling vectors, of multiplying a vector by a real number. It can be used to change the vector's length without altering its direction, or it can be used to flip the vector so that it's pointing in the exact opposite direction, depending on whether you choose to scale by a positive number or by a negative number. But scaling can also be done component-wise, and therefore it's relatively straightforward. Now to conclude today's video, let's look at 2 special vectors, which are called the standard basis vectors for 2-dimensional space. In 2-dimensional space, which is where we have been working, the vector labeled I with an arrow over it stands for the vector that has a 1 in the x component and a 0 in the y component. And j, with an arrow over it, the vector j, has 0 for x and 1 for y. These two are called the standard basis vectors for two-dimensional space. Now let's see what happens when we calculate something like 3 times I plus 7 times j. So scale I by 3, scale j by 7, and then add the results together. Now, just like with real numbers, PEMDAS is something that applies for vector arithmetic as well. The first thing that we're going to do is complete the multiplication, and then we will do the addition. So I'm going to multiply component-wise by 3, and 3 times 1 is 3, and 3 times 0 is 0. And I'm going to multiply component-wise by 7. 7 times 0 is 0, and 7 times 1 is 7. So when I add these two numbers together, I get an interesting result. I get a vector whose x component is an exact match to the scalar on I, and whose y component is an exact match to the scalar on j. So the standard basis vectors give us a way to express vectors symbolically without having to use the angle brackets. Instead of having a comma b in angle brackets, we can write the scalar a multiplied by the standard basis vector I plus the scalar b multiplied by the standard basis vector j. This notation, in my opinion, is more common in physics than it is in mathematics. In mathematics, we actually have rather funky ways of writing vectors. We don't use the angle brackets that commonly either. We have a bunch of other ways of writing vectors that are not given by this angle bracket notation or by the standard basis vector notation. But this particular notation is more common in physics. A times I plus B times J. That concludes today's material. We talked about vector addition, subtraction, and scaling. All of that was done component-wise, very convenient. Then we introduced the standard basis vectors and described how those could be used as an alternative to writing vectors in components with the angle brackets.